So how do we know an algorithm is incorrect? So let's answer this question now. So a problem is, you just think of it as a collection of possible problem instances. Each one has inputs and it has a solution, so upon being solved. So for example, we have the search problem. So imagine I give you an array A of n elements and an element x, which I'm going to call the key. I want to know if x is in A or not. If it's in A, I want to know where it is. If I don't know where x is in A, then I want to return -1, which is not a position in the array, right? So just to recap this, so now in the search problem, each one of my instances is one of these dots. Each one is going to be an array of length n. And for the sake of our discussion, I'm just going to presume that the elements are integers. So each one of those dots there is going to be some array of some finite length where all the elements are some integers. These can be positive, negative, and so on. So there's naturally going to be an infinite number of them. So just as an example of one of these dots might look like, see one of these dots, it could be this array. So imagine my array A looks like this. That's 5, 2, 3, 4, 21, 1, and 6. Just going to put my positions down. And suppose the key is 1. So this is an array of length 7. And it has, the key is 1. So I would like to know if x is in A. If it is, I want to know where it is. Otherwise, tell me -1. So for this example, where is 1? What position is it in? So I've labeled each one of the positions below the box. The box represents the array. Yeah, it's in position 5 here. So in this case, the solution is 5. So it tells me, so the solution in this case is 5. Why? Because 1 is in position 5. Naturally, if I switch this up and I put the key as, say, 8, notice 8 isn't anywhere in here, and the solution in that case would be -1. So all of my instances, these are all instances, by the way. The things I just described, those would be 2 dots in that weird shape I have over there. There's infinitely many of them. There's going to be all the arrays with all possible integers of length 1, length 2, length 3, length 4, length 5, all the way to any one finite number. There's infinitely many of them. So what does it mean then let's put it all together now. So let's talk about what an algorithm is in this context. So I'm going to draw a picture to help us kind of figure this out. So imagine I have one of those dots. For example, one of those. So imagine I have my inputs and I have my solution. And this is one of those dots. This is the problem instance right here. So I have a problem instance right there. So this is one of those dots. Just like, for example, over here, that input there would be A and X would be right here. The solution in this case would be 5. The problem instance is typically just the inputs. That's the encoding of the inputs. So naturally, I want to solve the problem. One way I could do this is using an algorithm. So an algorithm, naturally, it takes in inputs and it produces output. So this is given to the algorithm. And naturally, the algorithm does some process. It's a step-by-step procedure. It's what we call unambiguous. It means that there's no way you can misinterpret it. I mean, there's not 2 possibilities of interpreting this thing. Like, you can't misinterpret the procedure. So this is what we call unambiguous. It's an unambiguous step-by-step procedure. It takes an input, produces output. Now, I must stress that not every algorithm is going to literally produce output. Instead, what it will do is it might do some processing, and then it's conceptual that it has output. Say it computes some structure, for example, that you might use in the future. the concept still applies, it's just not maybe as literal as this. Now, a natural question then is, do these two match? Does the solution match the output? The solution. Are they the same thing? That's really the question here. So I told you that every one of the problem instances were in that weird shape, all those dots. So I pick out one of those, so I pick it up, and I give the inputs to this algorithm. It processes, gives me output, and I check if these match. So this is how I like to think about this. So imagine I have all my problem instances in this black bucket. And I'm going to have two buckets here. One of them is going to have it whenever I get a correct output. The other is going to have it when I get an incorrect output. So this big black one right here. I'm going to put it sideways to make it a little more distinguished. So anyways, what I should be able to do is pluck any one of those dots if I'm over there. Each problem instance. In this case, the search problem, it's going to be one of those arrays of length n, has some key. Each might have their own set of integers. The point is, when I give it to the algorithm, if it matches the solution, it gives me a plus. Cha-ching! It gives me a plus. I take another instance. Cha-ching! It's all good. However, if one of these does not produce the solution, it goes in this bucket. If that happens, then you know the algorithm is incorrect. Now let's put this in broader terms to make this a little easier for us to understand. So for an algorithm to be correct, it has to be that for every problem instance, the algorithm produces correct output, right? It has to match the solution. So that's what it means for an algorithm to be correct. It means it solves the problem. It means I pick up any one of those dots, it goes in this bucket. It goes in the cha-ching bucket. But what does it mean, what I just said? An algorithm is incorrect. Let's flip the logic of this. So for those that have some background in logic, you're going to look at the statement and be like, oh, Dan, it's really easy to negate this statement. But let me walk you through it. It's actually the same process we just did over here. Remember, I told you every one of the dots, I should be able to pick up any one of the problem instances. If the algorithm produces correct output, it goes in this bucket, right? It goes ka-ching, goes cha-ching. If it goes into this bucket, incorrect output. But remember, to be correct means that every one of the instances, all of these have to go in the cha-ching bucket, the one for which it produces correct output, right? So to be incorrect means that there exists one of these instances that goes not in the cha-ching bucket, it goes in the bucket. So that's all it means to be incorrect. So let's flip this around. So it says for every one of them, if I played a little game with you about how do I know if it's correct or not? Well, if somebody claimed that this was true, well, how would you refute it? You would say, okay, well, I could find you one such that it does not produce correct output, right? And that's exactly, you'd be exactly right. There exists a problem instance where the algorithm produces incorrect output. It does not match the solution. So for the given problem instances of your problem, then it has to be that it produces incorrect output just for one. It just requires one instance for this to happen. This is a very high bar, by the way. So if you can come up with an algorithm that can guarantee correctness like this, you're good. And that means that no matter how somebody picks up your algorithm and correctly implements it, it will still be It will correctly do what you expect it to, presuming that the person that implemented it was competent to translate your algorithm appropriately. However, if there's any one mistake that your algorithm can make, it gives you two pieces of insight. One, it's wrong. That's the first kind of most important thing. The second thing is that if there is a mistake, what we'd like to do is try to find some way of characterizing that mistake so we can better understand how we can fix the algorithm and make it so it does work correctly.